thermodynamics, we were looking at heat engines and the definition of efficiency of a heat engine. And then we looked at the particular case of the Carnot engine, which is a specific type of heat engine process involving two isothermal processes and two adiabatic processes. And we saw that that particular heat engine has a formula for the efficiency, which is 1 minus T2 by T1, or based on the temperature of the heat source and the heat sink, which are operating isothermally. So let's take it from that point ahead today. Yeah, so as I was saying, we were discussing that for a general case of a heat engine, the net heat absorbed by the gas during the cycle is some amount of heat supplied by a heat source minus some amount of heat which is absorbed by a heat sink. So Q1 amount of heat per cycle comes into the gas undergoing cyclic process, and Q2 amount of heat gets dissipated into a heat sink, and therefore the work done by the gas during the cycle is W. So W is equal to Q1 minus Q2, and the efficiency is defined as the ratio of work done per unit heat supplied by the heat source. So that can also be expressed as 1 minus Q2 by Q1. So this is the formula for efficiency of heat engines. Yeah, we will start heat transfer very soon, Snigita, after completing this portion. Okay. So we also saw that for a Carnot cycle, we had seen that Q2 by Q1 is equal to T2 by T1, which are the absolute temperatures at which the isothermal expansion and the isothermal compression take place. So this is part of an isotherm which is operating at temperature T1, and this is part of a isotherm at temperature T2. So the gas absorbs Q1 amount of heat during the isothermal expansion, and then it dissipates Q2 amount of heat during the isothermal compression. So Q2 by Q1 becomes this. So the efficiency is given by a special formula, 1 minus T2 by T1. Okay. So this is just a quick recap of what we had learned in the last lecture. Yeah, Vinith, there are different types of heat engines. So, for example, when you talk about the traditional internal combustion engine of fossil fuel, the efficiency process is still comparatively very low. It is in the region of the high 30s, 35% and above, not really more than that. Okay. Plus, in real engines, there is also further dissipative factors because of the non-conservative forces like friction and viscosity, etc., to overcome. Okay, so there are more dissipations to contend with. Okay. Now we can always get a situation where we have a different type of a process, which is a heat engine, not particularly a Carnot cycle, and we are asked to calculate the efficiency. So for example, we can have a situation like this where a more general type of a PV graph is given to us, and we have to calculate the efficiency. So as an easy example, let's take a case where there is a very simple rectangular cyclic process consisting of AB and CD being isobaric process, and of course BC and DA being isochoric processes. So if at the position A, the state of the gas is that the pressure is equal to 4 atmospheres, the volume is equal to 1 liter, and the temperature is equal to 200 Kelvin. At B, the temperature is equal to 600 Kelvin. Okay. At C, the pressure is equal to 2 atmospheres. We have to first of all find the state of the gas, that is pressure, volume, and temperature, everything at B, C, and D. And then we have to find the efficiency as a percentage. You have to find the percentage efficiency of the heat engine cycle. Okay. So very simple question. Let's begin with this. Try to work this out quickly. Okay, so this type of question you have to be able to do pretty fast. Okay, so the moment you put the data which is given in the question over here, this is 4 atmospheres, this is 1 liter, and this is 200 Kelvin. Okay. And the other data that is given is that this is 2 atmospheres. Okay. So immediately you can see the temperature of this point will become 100 Kelvin. Okay. So the quantities that I'm calculating, I'll just put in a different shade so you can understand. So these quantities are given, okay, and these quantities I want to find. So temperature at the point D. Now you can see that during this AD process, pressure is proportional to temperature. So pressure is half, so temperature will become half. Okay. During the AB process, volume is proportional to temperature. Okay. So the other thing that was given to me was the temperature at the point B, which was 600 Kelvin. So from this, I can now find out that the volume at the point B will become 3 liters because yes, Aman, very good. That's correct. Okay. And therefore, at the point C, we can see that the temperature, now the pressure, again here pressure is proportional to temperature. So the pressure is coming down by half, so the temperature should come down by half. And here to here, there should be 1/3 factor. Okay, so you can see that happening. So, so this becomes the first aspect. Okay, so I found out all the unknown quantities. Okay, now the crucial thing. So here to find the efficiency of the heat engine, second part, we can use the formula W by Q1 or 1 minus Q2 by Q1. Now here W is very easy to calculate. W is positive of the area enclosed. So in my mind, this is the easiest thing to calculate. So that is 2 atmospheres multiplied by 2 liters. So 4 liter atmosphere. Okay. So that is the net work done by the gas. Okay. Now as far as Q2 and Q1 is concerned, now the next thing you have to pay attention to, you can see that AB is an isobaric expansion. So Q is positive for AB. Okay. But BC is an isochoric cooling. The temperature is coming down. So Q is negative. Okay. Then similarly, CD is an isobaric compression. So this Q will be negative. And finally, D2A is an isochoric heating. So Q D2A will be positive. So Q1 will actually be the sum of the positive heat supply in AB plus dA, whereas Q2, the magnitude of heat withdrawn, will be the mod of QBC plus QCD. Okay. So this is something very important to understand over here. And the best way to visualize this is from the method I've given you, that if you visualize your PV space as a collection of isotherms, so as you're going away from the origin, your temperature is increasing. Okay, your temperature is increasing in this direction. So you can easily understand that which process involves heating, which process involves cooling. So you can understand that in this process, delta T is positive. In this process, delta T is negative. In this process, delta T is negative. In this process, delta T is positive. So you can understand Q is positive, Q is negative like this. Okay. So next we will calculate these values. So QAB is going to be N CP delta T. Now to calculate it, we should also be given which type of gas it is. Without that, we cannot. So given that the gas is, let's say, monoatomic. So given that, now we can calculate. So since it is isobaric, we can easily write this as 5 by 2 into, okay, pressure was 4 atmospheres and the volume difference is 2 liters. So as you can see, it's 20 liter atmosphere. Right, now similarly this process DA, this is an isochoric heating. So okay, so this we can write as 3 by 2 into the common, into the pressure difference into the common volume. Okay, so the pressure difference was 2 atmospheres and the common volume was 1 liter. So this will become plus 3 liter atmosphere. Okay. So finally, from this we can see that this will become 23 liter atmosphere. Okay. And therefore, you know that the efficiency will be 4 by 23. It should be, I think, around 17.4% if I'm not mistaken. Okay. So the thing is, you have got to be able to do these type of calculations and this type of analysis pretty fast. It's all very easy, but this chapter is all about accuracy and speed, so that you can not only gain the marks in the exam, but you can save the time for investing in more complicated questions from mechanics, electromagnetism, and those kind of chapters. So all these things should be in your fingertips. Okay. Okay, so in this particular question, we did not do the calculation of these values. But if you do the calculation of these values, you will realize that they will come out to be negative, and also they will come out to be in such a way that you can see from this that there's some, I mean, basically Q1 minus Q2 should come out to be W. So the W was 14, so this has to come out to be 19 in liter atmosphere. Okay, now we'll just do another example as practice to understand one more point about this, that sometimes it might be a little bit difficult to gauge whether a given process has Q positive or negative. So we have to be careful in that sort of a situation. So for example, we can have a PV graph given to us like this, which on its own looks very simple, but there is one tricky point in this. Just coming to that. Okay, so you can see that AB is isoporic, and Ca is isobaric. Okay, but BC is a non-standard process, some kind of an expansion. Okay, so again, suppose this is a diatomic gas this time, and excuse me, this pressure is 1 atmosphere, but the pressure here is, let's say, 4 atmospheres. And the volume here is, let's say, 2 liters, and this volume is, let us say, 4 liters, and the temperature at the point A is given to us as 100 kelvins. Okay. Now we want to find the efficiency percentage. Okay. So the slightly tricky thing here is the process BC. You don't know whether heat is, you can see W is positive for the process BC because it's an expansion, but we don't know whether Q is negative or positive because you have to work out the value of delta U and check that out. Okay. So this is where this question becomes slightly tricky. Just try it out. So for the efficiency, you have to find out how much is Q1 and how much is Q2, or how much is W. Okay. So that you can define efficiency as either W by Q1 or 1 minus Q2 by Q1, whichever be the case. Yeah, anybody got the understanding of this? You can see definitely in this process heat is coming in. Okay, QAB will be positive because it is a isochoric heating, and I can definitely see that in this process heat is coming out. CA, because it is a isobaric compression. But what about this third process? Yeah, work done is correct, Nikita. Work done you can calculate by the area. Yes, very good. That's correct. So that is the easiest thing to do here. So we need not calculate Q2 again, but still we'll need to calculate Q1 now. Okay, so work done is correct. Easiest way is positive of area. So half of the base into the height, which is 3 atmospheres. That's this much. Okay. Now for this we will have to get down to the proper thermodynamics. So we can see here that temperature at A is equal to 100 Kelvin. So temperature at B will be equal to what? It will be pressure at B upon pressure at A into temperature at A. Okay. So it will become 400 Kelvin. Okay. And we can see that temperature at C will become volume at C upon volume at A times temperature at A. So it will become 200 Kelvin. Okay, Kevin. So let's just verify that. So therefore, for BC, okay. So this will be N 5 by 2 R into TC minus TB plus half into sum of parallel sides. So that's 4 plus 1 into perpendicular distance between them in liter atmosphere. Okay. So I'm calculating the work done in the process BC by area method. But it's not area enclosed. It is a full area in okay, this area. This is the work done from B to C. Okay. So this will become 5 by 2 into TCBC minus PBVB plus 5. So that's 5 by 2 into product of pressure and volume, which is 4 liter atmosphere, minus at the point B it
minus
is
8.
Minus 8. Correct. Okay. So this is in liter atmosphere. So how much is this finally coming out to be? This is coming out to be
Minus 5.
Minus 5.
Minus 5 by 2, right? 5 into minus 3 by 2 plus 1. So minus 5 by 2 or minus 2.5 liter atmosphere.
So it's only minus 5.
Only minus 5.
Minus 5, is it?
Yes, sir.
Oh, sorry. Yeah, 4, not 5. Correct, correct. So this is minus 10 plus, okay, so minus 5 liter atmosphere. Okay. So this is crucial because without this information, I cannot calculate the efficiency, even though I've calculated the work done. because now I know that, okay, heat is coming out of the gas during this process. Okay, this is also negative. So Q1 will just be QAB, whereas Q2, even though we don't need to calculate it here, but it will be the mod of QBC plus QCA, because these two will be negative quantities. So anyway, so next let's calculate QAB. So QAB is nothing but NCV delta T. So that is N into 5 by 2.
Or delta.
Yeah, temperature at B minus temperature at A. So this will become 5 by 2 into the common volume into the pressure difference. So
PV
pressure
minus P
difference PB minus PA into the common
into 2
volume.
liters.
Okay, yeah, so this is 5 by 2 into this is how much? 3 atmospheres, correct? To volume 2 liters.
Plus 50.
So this is plus 15 liter atmosphere. Okay. So Q1 is this much. So this is the only information we need, because W we have already calculated. W for the cycle was this much. So now we can go ahead and calculate efficiency from this and this. So that's coming
20.
out to be how much? 1 by 5, no?
Yes.
So 20% efficiency. Okay, so this is just something you have to be a little bit alert about in these type of cyclic process questions, especially if there's some unknown type of process. Okay, it's a very easy process, straight line graph, but Aman 4 by 15 है कि 3 by 15 है? Work done was 3 ना बेटा? Okay. This W is work done for the cycle. Okay. So make sure you don't confuse this work done for the cycle with the work done during the process BC. That is this. That is plus 5, but this is plus 3. Okay, okay, good. Okay, so very simple. Like once you get used to these things, not very difficult. Okay, and of course you can have a cyclic process where one of the you can have a cycle where one of the processes is no, we did not need to calculate the complete value of QBC amount. That's correct, but we just needed to find out whether it is positive or negative. Once you establish this negative, it's fine. But suppose it had come out to be positive, then we need the value because it would be part of Q1. Understood, Amo? Okay. Yeah, and another type of thing is where your cycle has one of the processes being a polytropic process. So you might want to use the formula of polytropic process, which we've seen in the last lecture. So that's also pretty okay. You'll find it easy enough. Okay. Next, let's move on to refrigeration cycles and efficiency of a reverse heat engine or refrigeration cycle. So this is very easy again because it is just a heat engine in reverse refrigeration or reverse heat engine cycle. Okay. So here the schematic just looks like the heat engine schematic run in reverse order. No, not necessarily अमो. देखो टेम्परेचर कितने से डिक्रीज कर रहा है वो इम्पोर्टेंट है ना, बिकॉज that is the thing I wanted to establish in this example, that if you see the calculation of this thing that we've done, na QBC. Okay, so just pay attention to this part which I'm highlighting this now. This quantity is coming out to be negative, definitely, because the temperature is decreasing. But this quantity was positive because there was expansion happening, because delta T was negative. But that doesn't guarantee because volume was increasing. So for example, if the temperature had decreased to, let's say, instead of 200, it had decreased to 250 or 300 or something, then we might not have got Q as negative. We might have got Q as positive also. You're understanding now? We have to see which thing is dominating. So just because temperature is decreasing in a process doesn't necessarily mean that heat is supplied to the gas. Okay, if we extract too much work from the gas, then it can be the other way around also. So we might be extracting so much work from the gas that in spite of its temperature decreasing, you have to supply heat. Okay. Okay, so the schematic of a refrigeration cycle is, as I was saying, it is just like a heat engine run in reverse. So the cyclic process, in one cycle, W amount of work is done on the gas. So W cycle will be minus W because this is the net work done by the gas, which in a refrigeration cycle becomes negative, as you know. So here W is the net work done on the gas per cycle. Okay. And as a result of that process, Q1 amount of heat is extracted from the gas. But then some part of the cycle also involves Q2 amount of heat being supplied to the gas. So here the heat sink actually absorbs Q1 heat from the gas, and the heat source supplies Q2 heat. Okay. And Q1 is greater than Q2. So Q net for the cycle is also a negative quantity. So basically, Q cycle being equal to W cycle means that minus of Q1 minus Q2 is equal to minus W. So this relation still holds that W is equal to Q1 minus Q2. But the significance of each quantity is now reversed. W is the work done on the gas, Q1 is the heat extracted from it, and Q2 is the heat supplied to it. Okay. So the efficiency of this process, so what the reverse heat engine does is work is done on the gas or on the cyclic process to extract heat from it. Think of a compressor. Electrical energy is converted into mechanical energy, and that is part of the work done, by the compressor motor on the system. But heat is extracted from the inside chamber to the outside chamber. So if Q1 amount of heat is extracted, then the efficiency of the process is heat extracted per unit work done on the system. So here the efficiency becomes Q1 upon Q1 minus Q. So it is just inverse of the efficiency of the corresponding heat engine. If we run this cycle in reverse, then we will get the heat engine cycle. Now the arrows will all point in the opposite direction, and it will convert into a heat engine. Only this will go from the role of heat sink to heat source, and the lower part will go from the role of heat source to heat sink.
Sir, how did the efficiency get inverse of heat engine? I didn't get that.
हाँ, efficiency का यहाँ पे ना the definition became inverted because see the purpose of the refrigeration cycle is what we are extracting heat, and in order to extract heat we are doing work W on the gas. Understanding now?
Yes,
So the
sir.
output parameter here is the heat that we are extracting, and the input parameter is the work we are doing on the gas. No, so we are doing W amount of gas and we are extracting Q1 amount of heat from it.
Okay, sir.
You understood? No? So that efficiency of the process becomes the output upon the input. Whereas in a heat engine, it's the reverse. No? We are supplying Q1 heat from the heat source and we are extracting work from the gas. The gas converts heat into work. Here it is the opposite. We are doing work to extract heat from the system.
Yes, sir. Clear.
Okay, so that's why it becomes inverted. Okay. All right. Now, next thing we'll discuss something very important here is basically one form of second law of thermodynamics. The general form of second law of thermodynamics is a bit more extended, and we'll talk about that later also. But here we'll look at second law of thermodynamics for heat engines, okay, applied to the specific uh, science or engineering of heat engines. So it's a specific application of second law of thermodynamics, and that is that it's a simple statement. It's like a simple hypothesis that efficiency of a heat engine must be less than 100%, cannot be equal to 100%. So it's like a postulate. Okay, we cannot cross or we cannot reach the 100% mark. It's physically impossible. Just like in relativity, we have the postulate that a particle having non-zero mass cannot achieve the speed of light. It has to travel at a speed less than the speed of light. So like that, here we have efficiency of a heat engine must be less than 100%. Now, at our level, we are not going to get into any formal proof of it, but we are going to understand an explanation of it. So simple explanation of it is that for any heat engine operating between a heat source at temperature T1 and a heat sink at temperature T2, the maximum possible efficiency is when we run a Carnot engine. For a Carnot engine. Okay. So between these two operating temperatures, the maximum possible efficiency is equal to 1 minus T2 by T1. And T2 cannot be equal to 0 because 0 Kelvin is not physically viable. Cannot really achieve a temperature of 0 Kelvin. So the efficiency has to be greater than 1, sorry, less than 1 or less than 100% always. Okay. So this is a specific form of second law of thermodynamics which applies to heat engines. Yeah, so when we apply this to the reverse of this also means that refrigeration cycles have an efficiency always of more than 100%. So any reverse heat engine cycle will always have efficiency greater than 100% because it is 1 upon the efficiency for the corresponding heat engine. right? So this is just something factual you have to remember. Now, next up, we will move on to a part of thermodynamics, which is actually not in your JEE physics syllabus, but just for your understanding and for the general knowledge, I will just touch upon that. Okay. So that is the concept of entropy and the general form of second law. Okay. So we won't get into this in too much detail because this is not part of your JEE Advanced syllabus in physics, but you might have seen this in chemistry. Yeah, Shubham, I'll take you back to the above page. Yeah, theoretically, Danish, there's no such limit. Okay. But practically, of course, you can see from the formula of the efficiency itself that it cannot, be extremely large even. Just like, theoretically, we say that the heat engine can have efficiency up to 100%, but not equal to 100%. But that doesn't mean that practically we can achieve something like 99% efficiency or something. Practically, heat engines always have efficiency of quite a bit less. Okay. And moreover, when you study heat engines at the engineering level, especially mechanical engineering, you will see that there is a sub branch of mechanical engineering, which is thermal and fluids engineering. I mean, which is basically the courses within mechanical engineering. So you will see that there are a lot more complications in the engine design factor, and from that the efficiency process. So there are many more considerations. Here we are just looking at highly idealized, quasi-static reversible processes for ideal gases under very ideal circumstances and all. So, and without any non-conservative dissipative forces within the mechanical part of the system. So with all that consideration, we are just learning the basics of how to do these calculations. So anyway, so entropy is a very interesting physical quantity in general. Okay, entropy is a physical property, or it's a physical parameter, which is in fact a state function. Which is a measure of the degree of randomness, okay, or the degree of chaos of a system. Okay. This is the general definition of entropy. We'll come to the thermodynamic definition of entropy also. Okay. And the general statement of second law of thermodynamics is that the universe's entropy is always increasing. It's always going in one direction. Like time goes in one direction, it's always going the positive direction. Like that, the universe's entropy being a state function, it's always going in one direction. It's always increasing. Okay, but this is a bit abstract. and we will tone down this definition to thermodynamics. So this is a more abstract general definition. Okay. So there is a lot of other things like statistical mechanics, which is a more complicated version of thermodynamics put together with continuum mechanics, then probability theory, etc., that goes into all this. So we will avoid all that. Etc. So all that is out of scope for us. If you do graduate level physics or some branches of engineering, no, for any process, beta, any reversible, irreversible process, okay. But the direction in which a process will happen at the spontaneous level is determined by whether that results in entropy increasing or entropy decreasing. So I'll explain in just a moment, okay. So that is out of scope for us. But for thermodynamics, okay, please keep in mind that this is out of syllabus, this portion. I'm just discussing it a little bit because you might have heard of such things, or part of it might be in chemistry, so you should not get confused. Okay. So in thermodynamics, entropy, we denote it with a symbol capital S usually, and it's a state function, as I told you. Now entropy is defined in such a way that for any process, the change in entropy is given by a simple relation, that it is integration dq by T, where T is absolute temperature and dq is heat supplied to the system or to the gas that is undergoing the change. All right, so I'll just explain this concept of entropy increasing with a very nice and simple example to understand. So suppose we have this double walled vacuum chamber, insulated chamber. Okay. So the walls of the container are what we call adiabatic walls. That is, there is no heat exchange between the outside and the inside. But in between, let us say there is a partition which is made of some conducting material, so metal or something. So this is what we also sometimes call a diathermal wall. So diathermal means that it is a conducting wall. It's a heat conducting wall. Okay, and let's say it's a fixed wall. Now what we do is initially we place in this chamber a gas at temperature T1, and in the chamber B we place another gas at temperature T2. So our normal common sense and zeroth law of thermodynamics dictates that heat will be flowing in this direction if T1 is greater than T2 initially. Okay. Then the direction of heat flow will be like this. Okay. So in a small time dt, if dq amount of heat flows from A to B, then the change in entropy for is A is losing heat, okay, and the change in entropy for B is this, okay, and A plus B is an isolated system, okay, so that means there is no heat exchange with the surrounding. With the surrounding environment, or you can say with the surrounding atmosphere. So the surrounding atmosphere's entropy is not changing. So the universe's net entropy change as a result of this heat flow. Okay. The net entropy change of the universe as a result of this little bit of heat exchange between A and B during that small time dt is the change in entropy of A plus the change in entropy of B. So you can see it is minus dq by Ta plus dq by Tb. Okay. Now we can see that this net entropy change is positive because we know that Ta is greater than Tb. Okay. So this is the reason why we say that is why the spontaneous process is heat flow from A to B. Okay, when Ta is greater than Tb. Okay, the reverse of that process cannot happen spontaneously because it would have resulted in an entropy drop. Okay, and you will notice that there is no other law that actually defines why it cannot happen, because conservation of energy will still happen if we make heat go from B to A. But what is the underlying principle that we know as part of zeroth law of thermodynamics, that heat as a form of energy flows from higher temperature to lower temperature? But why exactly that happens? What is the underlying principle behind that? And that is nothing but actually the second law in the broader sense, that a spontaneous process will only occur in that direction in which the overall entropy of the universe increases as a result of that. So if we want heat to flow from B to A, when temperature of B is greater than temperature of A, then what we'll need to do is we will need to put a reverse heat engine between B and A, something like a compressor. So even when your air conditioner is working inside your room, which is at a lower temperature than the temperature outside, it still manages to throw heat outside from the lower temperature chamber to the outside atmosphere, which is at higher temperature. But it is doing that at the cost of something else doing work. So there is a system that is doing work on the compressor. That work is getting converted to part of heat, and heat is getting exchanged like that. So it is not an independent system in that sense. There is some external agent who's doing work, and that external agent's entropy will also be changing. So overall, the universe's entropy will still be increasing. But here, when we have an isolated system where no external agent is doing any work or exchanging any heat with this system of A plus B, then between A and B, the heat exchange will happen in such a way that the entropy must increase for the overall system. So that is the direction in which the spontaneous process will go. Okay. So there are some more interesting examples like this in Resnick Halliday, and you can read through them, or there are web pages about this and all that. So entropy on its own is a very interesting and fascinating topic. But as I said, you will not be asked this in your physics portion of JEE because it is outside the syllabus. Okay. However, I think especially for your knowledge in chemistry, you should know this aspect, what I'm describing over here now. Entropy change in a thermodynamic process. You should know this. And therefore, we will develop a further formula of this to show that it is a state function. Okay. So next up, you'll see that we are defining delta S as integration dq by T. So for an ideal gas, okay, going through a quasi-static process, we know that dq is equal to nf by 2r dt plus pdv, okay, and pv is equal to nrt. Okay. In general, dq is equal to du plus dw. This is the first law of thermodynamics, which is applicable to anything, not just quasi-static processes. Yeah, Vinith, I'll scroll back. Okay. So now if we apply this over here, so we can see that ds is equal to dq by T, okay, plus pdv by T. Now pv is equal to nrt. That means p by T is nr by v. So next, you will substitute this over here. So we will get ds is equal to nf by 2r dt by T plus nr dv by v. So the change in entropy during any process becomes this, okay, from initial to final. So the formula for change in entropy for an ideal gas undergoing a quasi-static reversible process now becomes more specific. And from the formula you can see it is independent of path. It only depends on state. You can see that the value of delta S, it is a state function. Okay. Only depends on initial and final state. Okay. It is path independent. Okay, so in my opinion, you should be familiar with this formula also, even though it is not directly in your JEE syllabus. Okay, you can always get a paragraph question where the paragraph explains to you this, and you have to finally work out this application from that paragraph in JEE Advanced. So you should be familiar with this, according to me, even though it is not directly in your syllabus. Okay, so just go through this one, and I will take you back to the earlier page in just a moment, Vinith. So entropy is expressed in joules per Kelvin, that you can see from the dimensions of this equation. Okay, very good. Okay, so this completes the first law of thermodynamics applications, heat engines, and a little bit about second law. Now we will very soon move on to the the last part of heat and thermodynamics, which is about heat transfer. But before that, I want to do one more type of question. Okay, one more type of question specifically for application of first law, which involves a bit of mixed concepts. So I'll come to that. Finish writing this down first. It is independent of path. It's a state function, so it is path independent. Okay. So basically on the PV graph, if we get from some initial point to some final point via two different paths, the entropy change will be the same, because ultimately there is some initial state and some final state. And you can see the formula involves only the state functions. The ratio of final to initial volume, right, and the ratio of final to initial temperature. You can also write F by 2R as CV. So this term here can also be written as NCV, natural log of this ratio, plus NR. Okay. Yes, okay. So this is another way of expressing the same thing. All right, now, yeah, so as I was telling you, one more tricky type of example I want to discuss. So once again, we have our sort of insulated cylinder kind of thing. But this time we have a heavy piston. And instead of loading the piston with mass, what we are going to do is we are going to attach a spring, an ideal spring, the type you studied about in Newton's laws a few days back. So these are adiabatic walls. This is a free but adiabatic piston. There's some kind of ideal gas inside. Let's say it's monoatomic. And there is some kind of heating element. So this piston is also heavy. So the piston has a mass of, let us say, 10 kilograms. We'll take G as 10 meters per second square. And it has an area Just a second. Five centimeters square. Okay. The spring constant is an ideal spring. So the spring constant is 50 newtons per centimeter. Atmospheric pressure is equal to 1 into 10 raised by 5 pascals. Okay. So initially, the gas inside is at temperature of 200 Kelvin, pressure unknown, and a volume of 100 centimeter cube. Okay. And the spring is in relaxed state. Okay. So first thing, find this pressure P1. Okay. Now second part, now heat is slowly supplied through the heating element, okay, till the gas expands to, let us say, 120 cubic centimeters. Okay. So find final state of the gas, that is pressure and temperature, and heat supplied, Q. Yes, Kevin, that's correct. Very good. Okay, now one thing here is you assume that the piston doesn't come out of the cylinder. Okay. Like as we expand the gas, the cylinder's walls are tall enough. Okay, so, or basically you can modify the diagram a little bit. Just show that the initial position of the piston is a bit more inside somewhere here. The spring is of course attached to it. Yeah, so Tanish, just convert that to pascals or atmospheres. That's not correct. So the hint to use, you'll always get the pressure of the gas, the internal pressure of the gas, by making the free body diagram of the piston. So remember, the piston is in equilibrium. So the upward force acting on the piston because of the pressure of the gas has to balance the downward forces which are acting, which include the weight, atmospheric pressure, if there's any spring force, etc. Yes, Nikita, that's correct. Very good. Yes, Naman, that's correct. Very good. Okay, so let's look at the first part. So if we look at the state of the piston, the first part of the question, remember that the spring is in its natural length. So the spring is not applying any force on the piston. So P1, V1 is equal to 100 cc and T1 is equal to, how much was it now? 200 Kelvin. Okay. So this is the initial state and the spring is at natural length. So X is 0 for the spring. Okay. So when we look at the force picture here, you can see on the piston, there is a force that the gas is applying, which is P1 into the area. The force due to atmospheric pressure from outside, which is atmospheric pressure into area. And of course, there is the piston's own weight, mg. So initially, see that F1 is balancing this. So P1 into area is equal to P0 into area plus mg. So the initial pressure is atmospheric pressure plus the pressure due to the weight of the piston. Okay, so in pascals, that is this much upon, okay, Okay, Kevin, I will just check your answer. Seems correct. Pressure is definitely correct, the second one. Okay. So this will be in Newton per meter square, which is the same thing as pascals. So 3 into 10 raised power 5 pascals, or P1 is equal to 3 atmospheres. Okay. Yes, Aman, that's correct. Very good. Okay. Now from this state, we will see next up what is happening. We are supplying heat to expand the gas such that it goes from this state So I've expanded the gas from a volume of 100 cubic centimeters to 120 cubic centimeters. Okay. So the displacement of the piston, whatever that is going to be the compression of the spring. So the spring is now in compressed state. So there's a spring force Kx, there is the weight mg. So the internal pressure has to increase, because as you can see, there is one extra force now. Okay. So the final pressure is atmospheric pressure plus mg by A plus kx by A. Now you can see that V1 was area into whatever that earlier length was. So L0. That was equal to 100 cc. V2 is area into the new length, which is 120 cc. Okay. So E into X is V2 minus V1, the change in volume, which is 20 cubic centimeters. So X is 20 centimeter cube divided by the area, which was given to you as 5 centimeters square. Right? So X is 4 centimeters. Okay. So that is what we have to substitute here. Okay. The area of the piston was given to us as this. Okay. And the spring constant was given to us as, how much was that now? 50 newtons per centimeter. So when we substitute this information here, this becomes, these two we've already calculated. Now this kx becomes 50 newtons per centimeters into 4 centimeters. So that's 200 newtons divided by, okay, so 7 atmospheres. Okay, and now from equation of state, we'll get the temperature. Yes, very good, that's correct. So T2 will be P2 by P1 into V2 by V1 times T1. So 7 upon 3 into 120 by 100 into 200. 560 kelvins. Okay, so the final state is this: P2 is 7 atmospheres. The volume, of course, was given to us 120 cubic centimeters, and the temperature has increased to 560 Kelvin. So this is the answer for the first part. Now comes the tricky part. For the second part, you want to find Q. So just the state is not going to be enough, because Q is a path function. So you'll have to understand, how to calculate the work done. Okay, so just to give you a hint, there are a couple of ways by which we can calculate work done. One is by the definition, it is integration of PdV. So just like we have written a formula for P2 now, in the final state, we can write a formula for P as a general function of X, where the displacement of the instantaneous displacement of the piston is, let's say, X, and that X is increasing from 0 to whatever 4 centimeters. So that's one way. The other is we can also logically understand the work done by the gas, where that work is going into, what kind of energy it is getting converted into. For example, it is getting converted into gravitational potential energy of the piston, because that's increasing. It is getting converted into elastic potential energy of the spring. So we can use a sort of mechanical work energy theorem kind of concept also.
not able to hear you.
Okay, Kevin, let's work this out. Anybody else got the answer? Aman, your answer is in joules. So one way is that we take this sort of diagram only, but we take an instantaneous value. So at some intermediate time, we just take okay. So P into A is balancing because this is moving very slowly because heat is supplied very slowly. So the acceleration is tending to zero. So okay. So we can write the instantaneous pressure as this. Okay. So the work done by the gas for a small displacement of dx, the work done by the gas will be PdV. So that is P into A into dx. Because the area at any instant is L naught plus x. Sorry, the volume is area into L naught plus x. Okay. So the change in volume for a small displacement is going to be E dx. So, so work done, which is integration P dV, will become integration of P into A into dx. So that will become integration of P naught plus mg plus kx dx. This will be the expression for work done. from the initial state where x was 0 to the final state where x is equal to whatever x final, let's say. So that is 4 centimeters. So we get this kind of term. Okay. So the formula for work done that we get over here is this. Okay. Now E into x final is 50 centimeters square multiplied by, or was it 5 centimeters square? It's 5, no? Yeah, area of cross section is 5. So that's 20 centimeter cube. Okay. Then, so this term becomes 1 into 10 raised power 5 into 20 into 10 raised power minus 6. Then mg was 100 newtons multiplied with x final, which is 4 centimeters. This is in newtons, this is in pascals, this is in meter cube. Plus half, now k we'll have to convert. So k was how much? 50 Newton per centimeter, was it? Yeah. So 50 Newton per centimeter. So that is 5000 Newton per meter. Okay. Into 4 centimeters square. So this is Newton per meter into meter square. So everything is in joules. So let's see what we get for the work done by the gas. We get it as 2 for this one, right? Plus 4 for this one, plus 5 into 8 into 10 raised power minus 4 plus 3, so minus 1, so 4. So I'm getting the work done as 10 joules. Just check the answer. Kevin, is that the answer you got? No, no. Or work done? So I think you missed out the work done against atmospheric pressure part, maybe. Is that the case? Okay. So you got only these two terms, mgx final and half kx final square. Okay. But anyway, so this is the logical definition kind of way of calculating work done by just using the definition of work done by the gas. Now I'll show you how we can shorten the steps a little bit also by using a sort of logical method. Okay, but first make sure you understand this. Okay, got it. Don't worry. Okay. Now we still have to calculate delta U, so I'm coming to that. But the thing is, even this calculation, we need not have done so much. I'll explain how we can do this in a different way. This part, we can apply an alternate method. But first, make sure you're clear with this. So this is the for work done method 1 we are applying. Work done is by definition. Okay. So P is some kind of function of x and dv is a dx. So it comes by integration. All right. So the alternate method of calculating work done is by using work energy theorem. So for that, what we'll see is, if you look at the piston plus the spring attached to it, okay, plus gravity as a system, okay, then work done by the gas plus work done by the force due to atmospheric pressure is equal to change in kinetic energy plus change in gravitational potential energy plus change in elastic potential energy. Okay. So in this case, the work done by the gas is W, which I want to find out. Okay. But the work done by the atmospheric pressure force is very simple because that force is constant. Okay. So this will just become P naught A into delta X or X or whatever, where X is the vertical displacement. Where this moves by. Change in kinetic energy is 0 because it's a very slow process. Plus mg x final, okay, plus half k x final square because x initial was 0 for the spring. So you can see it's the same thing. The work done by the gas, oh sorry, this is doing a negative work because this force is acting the opposite direction. So this work done is minus F naught into x. Okay, so that is minus of this. Okay, so you can see it becomes or you can say it is P naught into change in volume. So this is the work done by the gas, which when we calculated came out to be 10 joules. Okay, so now that this alternate method is clear, now let's calculate the Q. So Q will be equal to delta U plus W. So delta U, we had taken a monoatomic gas as far as I remember. So it is N into 3 by 2 R. Okay, so you can just write that as 3 by 2. P2 V2 minus P1 V1. So final pressure was 7 atmospheres and final volume was 120 cc. So that is so 0.12 into 10 raised power minus 3 liters. Minus P1 V1, which was 3 atmospheres into, so this will be in liter atmosphere. So just convert that here. Now here we have taken 1 atmosphere as 10 raised power 5 Pascal. So we will be taking 1 liter atmosphere as 10 raised power 2 joules. So I'm getting delta U as some 71 joules. Just check my calculation. You people seem to be getting some different values. Kevin, you got something similar, no? Jewel, you got 81. Okay. Sorry, it's 81. My mistake. Yes, it is 81. I'm using the value of atmosphere as given in the question. Okay, atmospheric pressure was given in the question as 1 into 10 raised power 5. So I'm not taking it. I'm not taking liter atmosphere as 101 joules. I'm taking it as 100 joules. So I'm getting this round figure. So Kevin, you might have taken 101 joules now for liter atmosphere. That's why. Okay, so Q finally is becoming 91 joules. So this is also a question from which you can understand the whole concept of first law, how it is being applied. So what is happening? You are supplying 91 joules of heat. Now out of that, 81 joules of heat is going into the extra kinetic energy of the gas molecules, because that is the internal energy. The gas molecules start moving about faster, their temperature increases. So 81 joules goes into that, and the remaining 10 joules, it is going into pushing the piston up, so its potential energy is increasing. The spring is getting compressed, so its elastic potential energy is increasing, and we are doing some work against the atmospheric pressure. So this work done by the gas, it is equal to the work done against the atmospheric pressure plus the change in gravitational potential energy plus the change in spring's potential energy. Yes, Somarup, I will scroll up. So with this, we complete today's session. So next session we will be starting heat transfer. So we'll start with heat conduction. Now heat conduction is both a very easy but also an important part of heat and thermodynamics. And some of the things we'll learn about heat conduction will be very similar to circuit analysis for current electricity later. The process of heat conduction through a heat conductor has certain similarities with the process of electrical conduction through an electrical conductor. Okay, so that's it for today's session, people. Wish you all the best. And I think we have a doubt session sometime this week. So please collect your doubts and we can do some questions from HC Verma and module of heat and thermodynamics also. Or if you have anything left over from mechanics or even in the other chapters of mechanics, rotation, etc., keep the doubts ready. We will discuss them on the, I think it is Thursday morning or whatever. Okay. All right, people. Wish you all the best.